Here we have a second order linear differential equation, a2 of x y double prime plus a1 of x y prime plus a0 of x y is equal to 0. We saw in the previous set of videos that such an equation has a fundamental set of two solutions. If we call y1 and y2 the functions that form that fundamental set of solutions, then by definition, they're linearly independent. So if we have c1y1 plus c2y2 is equal to 0, and we make the assumption that c1 and c2 are not 0, we can write y2 is equal to negative c1 over c2y1. And you may say, well, that's going to contradict linear independence. And so we then presume that negative c1 over c2 is not a constant, but a function of x. We can then rewrite what we have as y2 equals u of x times y1, where u of x is some unknown function of x. Our second order differential equation in standard form is y double prime plus p of x y prime plus q of x y is equal to 0. Now, let's suppose that we know what y1 is. y1 is a known solution. Then we suppose that y2 has the form u of x times y1. Now we're going to do something that is going to become a familiar pattern throughout the course, which is we have identified the form of solution or a proposed form of solution, and we're going to differentiate as much as we need to, plug it into the standard form equation, and see what shakes out. I'm not going to keep writing u of x, but u is a function of x, and y1 is a function of x, as it's a solution to the differential equation with independent variable x. Therefore, for y2 prime, we have u prime y1 plus u y1 prime from the product rule. For y2 prime, we end up with u double prime y1. Some terms collect, and so we have 2u prime y1 prime plus u y1 double prime. If we now substitute, then y double prime plus py prime plus qy equals 0 becomes u double prime y1 plus 2u prime y1 prime plus u1y double prime, now that's from y2 double prime, plus pu prime y1 plus pu y1 prime, now that's from p times y2 prime, plus qu y1, and that's from, of course, qy equals 0. I think I read a u1y1 double prime in there. There shouldn't have been a u1. There's only one u here. Now, if we take all of the terms that have u in them, we can collect u times y1 double prime plus py1 prime plus qy1. But we knew that y1 was a solution to the differential equation, and the differential equation has a right-hand side of 0. Therefore, all of that is equal to 0. And what we have left can be written as u double prime y1 plus, with all the terms containing u gone, 2u prime y1 prime plus pu prime y1 is equal to 0. And we can express this in terms of u. We've got u double prime y1 plus 2y1 prime plus py1, that whole thing times u prime equals 0. What we now have is a second order differential equation where u is the unknown function, but it only appears as u double prime and u prime. There's no plain u anymore. So we're going to make a substitution. let W represent U prime. Then what we'll have is that W prime is U double prime. I know that's a weird thing to hear, but substituting is going to give us W prime Y1 plus the quantity of 2Y1 prime plus PY1 times W is equal to 0. And what we now have is a first order differential equation in W. We took what had been a second order differential equation with U and turned it into a first order differential equation with W, and we have thus reduced the order of the differential equation through the substitution W equals U prime. That's the name of this textbook section here, reduction of order. This substitution allows us to reduce the order. As it happens, this equation is linear and separable. We're going to approach it using a separable approach. So we have W prime over W plus, in parentheses, 2 times Y1 prime over Y1 plus P is equal to 0. Now, if we trace back what these functions are, remember P came from the standard form of the differential equation. It's actually a function P of x, so it's a function of x. Y1 was a known solution to the differential equation and is also a function of x. W is U prime, but U prime was again a function of x. So this whole thing is a function of x. So we're going to solve this by integrating the entire thing with respect to x on both sides, although the right-hand side is just going to give a constant. And what we have is the natural log of the absolute value of W plus 2 times the natural log of the absolute value of Y1 equals the negative of the integral of P of x dx, where I've rolled what would have been the constant on the right-hand side into that integral of P of x. Now, using properties of logs, we have natural log absolute value of W y1 squared is equal to that negative integral P of x dx. And exponentiating both sides is going to give us W y1 squared is e to the negative integral P of x dx. Isolating W is going to give W is equal to e to the negative integral P of x dx divided by y1 squared. Our earlier substitution had been that W is equal to U prime. That's going to give us that U is equal to the integral of e to the negative integral P of x dx divided by y1 squared, all integrated with respect to x. Now this is a funky looking integral, right? It's an integral that contains an exponential that itself has an integral in the exponent. But when you compute this, you just do it basically following the order of operations. Inside the exponent of the exponential, you have the integral of P of x dx. Don't forget that minus sign. So we integrate P. It's now an exponent on e. We already knew what y1 was, so we have y1 squared. That whole thing is just a function of x, which we then hope we can integrate. Now that gives us u. But remember earlier we said that y2 was equal to u times y1. That leads us to the reduction of order formula. y2 is equal to y1 times the integral of e to the negative integral P of x dx divided by y1 squared times dx. It's one of the more complicated formulas we've seen, and yes, I'm going to say you need to know this. I'm also going to say you need to know how this process goes. It's not the case that I'm going to ask you to do this symbolically using u and some unknown y1. You'll see how it goes as our work progresses, but really what you need to remember is that y2 is equal to u times y1. U and y1 are both functions of x, so when we differentiate them, there's the product rule, and when we differentiate it again, the product rule shows up a couple of times and some terms combine. That substitutes into the standard form, and then from there, W is equal to U prime, and you look at the differential equation you have there, and solve it based on what you know from previous lessons. Now, a note about a couple of things. Number one, there's this constant of integration that we didn't bother with, and there's the absolute value of w that just kind of disappeared. Remember that y, the solution, is going to be a superposition, a constant c1 times y1 plus a constant c2 times y2. y2 is this thing that we've just gone through this process to find. If there had been a constant of integration here on the right-hand side, really I guess it would have come from the integral of 0 dx, then because of what we know about properties of exponentials, that would have showed up as a coefficient on this e. Furthermore, if we had kept the plus minus in front of w, we would just roll that in front of the constant. That constant would come out as the constant multiple rule in front of this integral. It would live inside of u, if you will. We have u, which is inside of y2, and y2 is being multiplied by a constant. And so this constant right here actually eliminates the need to consider those details. Bottom line here, we have a process and we have a formula, and then the next video we're going to start to see how we use them.